I'm Anil Kumar. Welcome to my series on Combinatorics. Here is an excellent video on Pascal's triangle. We'll introduce Pascal's triangle, look into some of its properties, take examples while going on, and also some practice exam questions. We'll see how it is related with binomial coefficients and how does it help to expand a binomial. Let's begin with the triangle, which you see on the right side right there. The numbers written are very interesting. What you notice here is that we have ones on the boundary, right? Both sides of the boundary have number 1. And in between numbers can be calculated by adding the previous two. So if you add the previous two, 1 plus 1, for example, gives you 2. 4 plus 6, for example, gives you 10. So likewise, you could enter all of the numbers within the triangle. So every number in between those ones is actually obtained by adding previous two. So for example, if I add the number 1 and 2, what I get is number 3 right under it, right? That is how you can fill this up. It's very easy to create this triangle with the numbers filled in. And this triangle is known as Pascal's triangle. Perfect. Now it has so many usages that the whole chapter of combinatorics can be dealt with its proper understanding and has huge application in mathematics. So in the name of this mathematician Pascal himself, we call this triangle Pascal's triangle. As described, the triangle is bordered by ones and the numbers in between are the sum of two numbers closest immediately above. So the entries in the triangle can easily be generated as we have shown. Now, we have already filled in up to this row where you see the numbers 1, 8, 28, 56, 70, and so on. Understanding this particular rule will like you to explore, try to extend the given triangle by adding another row. So let's move on and see what exactly this triangle is. So this triangle has identified elements with rows and diagonals, right? So these are the two. Like rows and columns, you identify a table with. Pascal's triangle is identified by row number and the diagonal number. And you'll notice that both row number and the diagonal number begin with row 0, not by 1. So row 0 and diagonal 1. So the very first element here, which is called the term number, will be T00. So that is how you write it. So that is how you get each and every term inside the triangle. So all these small units which you see are called terms. Correct? And they're normally written with T. First you write the row number. So we say N and then we say diagonal number, but we write R there. T and R. Both N and R, they begin with 0, right? So for example, the element which is, let us say, let's keep some elements. So let me color this one. So this element will be what? We'll call this term as starting with 0. First we'll write T for it, correct? And now starting with 0, 0 row, 1, 2, 3, 4, and that is fifth row, correct? So this is your fifth row. So we'll write T5. As far as the diagonals are concerned, we have 0 diagonal, 1, 2. So diagonal 2. So that is how that term will be represented. So that is the term number. T5, 2. Perfect. So I got an idea, right? That is how we could do it, right? Now, how do we get the value of this? T5, you could get the value by adding the previous two, right? So the previous two here should be the one before. Let me highlight those now. So those will be these two. Perfect. And these two should be what? The value on the left side will be t, a row before that, so 4, correct? And it is the first diagonal, right? So that, and on the right side, it is the same diagonal, correct? So it will be t 4, 2. So those two will combine to give you the next row element, which will be t5, 2 in this particular case. So I hope this concept is absolutely clear. Now let's look into what is written here. Iterative formula for Pascal's triangle. So this formula, which I just showed you, can be followed and repeated, and therefore we call it iterative formula. Each term in the Pascal's triangle is defined by row n and the diagonal number k. Intersection of the row and the diagonal number is the position r, right? So term number r, right? T and r. Now, if T and R represents the term in row n and position r, then T and R will be what? It will be sum of Tn minus 1 r minus 1 plus Tn minus 1 r. So that is the formula for getting the next term in Pascal's triangle. Correct? You should note that row, diagonals and position begins with 0 in the Pascal's triangle. So clearly I have written all the row numbers and the diagonal numbers, and that gives you the term in between, which is defined by the row number and the diagonal number. Clear? Let's take up example to understand everything which we have learned so far. Example 1 will use the Pascal's method which we just learned. How do we get the value or the number of the element in between, correct? So what I've done here is filled up to the 9th row, which will be treated as the 8th row as a row number for Pascal's triangle, right? But there are 9 rows in all, remember that. So row 1, 2, 3, 4, 5, 6, 7, 8, 9. However, we'll say this is row 8 for Pascal's triangle, right? So 1 minus, because the first row is row 0. Remember that part, correct? So this is critical to understand. Now, the example here is use Pascal's method to write the formula for each of the following terms. So the first one is T10R. So how can you get the value of T10R? That is the first question, right? So T10R, we have to add the previous two to get this, right? You can pause the video, answer this particular question, and then look into my suggestions. So to get T10R, definitely we are going to the previous row. So let me write like this. We know previous row. So 1 before this will be 2, and the one just above this will be 3. And that is how you get your answer. So that will be the value for part A. And that is how you have to answer the other two. So that is a practice exercise for you. Write down how will you write T 9980 and in general Tn plus 1 r plus 1. Okay, so you can use the Pascal's method, which is the iterative formula that Tnr is equals to Tn minus 1 r minus 1 plus Tn minus 1 r. Correct? Let's move on and take the next example. Example number 2 is also based on the formula we just discussed. Use Pascal's method to write the value of the following terms. Well, to get this value at present, first thing is try to build your triangle, right? So take a moment, make or create this triangle with ones on the boundary as shown here and the inside numbers by adding the previous two. 1 plus 1 will give you 2. Then come to the next row. So 1 plus 2 will give you 3. Again 2 plus 1 is 3. Then you can go to the next row. 1 plus 3 is 4 and continue like this. In this fashion, you will come to any number of rows you can add, correct? That is the whole idea. You can always pause the video, answer this question, and then look into my suggestions. Now, here is my answer. First, let's try to find out what is T85. T85 we can read directly from this particular Pascal's triangle which we have created. So that is the row which we are looking at, and T85 will be starting with 0, 1, 2, 3, 4, 5 is this particular term, so it is 56. Now, so we got this one which is equal to 56, and now let's look into T95. Now T95 will be sum of T84 and T85, correct? Now T84 is for us 70, right? So it is 70 plus T95 is 56. And when you add them, you get 126, which is the correct answer for T95. So we get T95 as 126. Let me write down 126 as T95 under this. Now let's find out what is T105. Now T105 is going to be T94 plus T95, correct? So that is what it is going to be. Now we know T95, which is 126. Now what is T94? So let's look into T94 now. 0, 1, 2, 3, 4. That means we have to add again 70 and 56. So that will also be 126. So we'll add 126 to 126 to get our value, which is 252. So this value will be 252, correct? So we have our answers which are as shown here. So I hope that makes sense. So you need to extend this Pascal's triangle to get the other values for the moment. We'll also learn a shortcut method of using calculator to find these values. Now let's take example 3, which is again based on Pascal's method expressed as a single term from Pascal's triangle. So basically, we are going to use the definition which is right there to answer this particular question. I'd like you to again pause the video, read the question properly, answer, and then look into my suggestions. Take a moment. Well, let's go through it. So the very first one, which is T12.5, 12,5 plus T12,6 is what? So definitely, we are looking into this. They will add, and you get the next row element, which will be T13, 6, correct? So that is how you're going to get it. So this is equal to T13, 6. Is that clear to you? The next one here, we have written as a something minus something. How will you work with this? Okay, let's look into this. So the next one is T53, 29 minus T52, 28. So minus means we have taken something to the left side. That means we have rearranged the values, correct? Now, so T53 is higher, so I could always write this as T and R. Take away one of these elements, 52, 28 they are taking. So that means I'll take away Tn minus 1, R minus 1. I'm left with Tn minus 1 R, and therefore that should be equals to T52, 29, correct? So that becomes the next answer, which is T52, 29. Is that clear to you? Correct? Now the next one is, what is the value of T and R minus Tn minus 1R? So that is the rearrangement of the formula itself. So let me rewrite this as T. So n minus 1, of course. And since we have already written R, I'll take the other element on the left side, which is R minus 1. And that is how we get answer for this particular question. So I hope you have understood the concept of getting to the next element in Pascal's triangle, correct? So I'm using different words, next element, next term. These are all the terms which can be used for the Pascal triangle numbers. Now here is first test or examination style question for you. Now in examination what you will see is that you'll be given some numbers from in between, and then you have to figure out what is the number which is missing. So fill in the missing numbers of this part of the Pascal's triangle. You're given 36, 84, 126 with their placement and 210. So these are the places where you have to mark or write down the numbers which are missing. So take a moment to answer this particular question. The concept is absolutely clear to you. What you need to do is add these two to get the next value. Is that clear to you? So when you add that, you get what? So you get 36 plus 84 for that particular answer. And when you do that, this is 10 and 1, 4, and this 120. So this value here will be 120. So likewise, you have to fill up all this. The element here will be what? Well, this time you have to see what number will add to 84 to give you 210. So in this case, you have to subtract from 210 the number 84, and when you do that, what you get is 126. So this number here will be 126. You get the idea. So that is how you have to continue, fill in the numbers, and get the result, right? So it's absolutely clear. The next number here will be addition of these two, 126 and 126. When you're going to add, you get 252, correct? And then follow with more addition of the numbers before, and that is kind of a practice for you. So 210 and 120 will give you 330. Similarly, we can get the next number now by adding 210 and 252. So that gives you 462 as the next number. So that is how you're going to get the answer. Let's take up the next question, which is example 4. Explore patterns in the Pascal's triangle. So here is your Pascal's triangle where I've mentioned the rows and the diagonals. I've also marked few numbers in different colors. So we have 4, 6, and 10, for example. So as you know, this particular thing gives you sum. 4 and 6, when you add, you get the next element. And that is how you actually get the next element, right? The value of the next element. So you can fill the whole triangle using this pattern, correct? So add previous two and get the next one. That is one thing, of course. But when you're looking at this pattern, there are so many ways to look into. Some of them are listed here for you. For example, calculate the sum of each row. What do you figure this out? Well, if I have the sum, this is just 1, correct? When I add these two, what do I get? I get 2. 1 plus 2 plus 1 is 4. And then 1 plus 3 plus 3 plus 1, 3, 3, 6, 7, 8, right? So we get 8 here. And the next one, 1 plus 4 plus 6 plus 4 plus 1, 6 and 4 is 10 and 1, 11, and 5 is 16. So you get this. So what you notice here is that all these are 2 to the power of 0 is for 1, right? So we could write this as, as 2 to the power of n. So 2 to the power of 0 for the first one, 2 to the power of 1 for the first row. First one row means 0, right? Row number 0. So where n is the row number? So that is how you get the sum of the row, which we figured out is 2 to the power of n. Symmetry. Well, you can clearly see the symmetry that the values from the left side and the right side are similar, right? So that is about the symmetry. Then triangular numbers. Well, triangle numbers are that if you start stacking up the triangles, right, something like this, then how many triangles do you get? Beginning from 1, right? So if you kind of stack this up like this and then further, correct, then the number of triangles, I'm making circles here, but you could make the triangles. And so what numbers do you get? 1, 3, and this is 6. You will notice all these triangular numbers are along one of the diagonals which is the third diagonal, which we write as diagonal 2 for numbering the term numbers. So this is a very important diagonal which gives you the triangular numbers. Similarly, if you stack oranges in a pattern, you can get tetrahedral numbers which are shown here in the next diagonal, correct? So those are the tetrahedral numbers which you could actually get. So let me just show you orange color on the side. So that is how it is. Many important things you can see from here. Diagonal sum. Okay, so if I add 1, 2, 3, and 4, what do I get? Well, that is 10. You see that? 10 is also there, but it's diagonal next to it. So that is how you could add diagonals and get some values. So those are the diagonal sums. It gives you kind of a structure like a hockey stick. And so we have a hockey stick property of Pascal's triangle. You can also figure out some perfect squares from here, especially looking into the third row itself. If you combine any two elements, for example, 1 plus 3 is 4, and 4 is a perfect square. 6 plus 10 is 16, which is again a perfect square. 15 plus 21 is 36, which is a perfect square. That is how you could do it, and this is left for you. We are going to take up some questions based on sum of squares. That is to say, we know 1 plus 3 plus 3 plus 1 is 8, but what about 1 square plus 3 square plus 3 square plus 1 square? Is that sum also given somewhere? Well, let's figure this out. 9, 10, and 1. So 1 plus, this is 9. Let me write down this as 1 plus 9 plus 9 plus 1, 10, and 10 is 20. We do have a number 20 here, which is right there, right? So relate this to that number right in the center. You will see a relation and a pattern. You can define this pattern, and so sum of each row is also provided in the Pascal's triangle. So there are many examples which you could explore here, right? So it takes a moment to explore few patterns in Pascal's triangle. Now here is the hockey stick identity which I was talking about. We just explored this, right? Do you see those curved diagonals? So we have the first diagonal shown moving in this fashion, which is diagonal 1. When we name it with Pascal's triangle, 1 plus 2 plus 3 plus 4, sum of natural numbers, right? Starting with 1, of course, you get 10 as the sum, which is diagonally placed, as shown here towards the right. Now, if you look from the other kind of diagonals, which start from 1 on this side, the left side, then the sum is provided on the left side of the diagonal, next row, as shown here, right? This is called the hockey stick identity. The sum of the elements in a diagonal line starting at 1, this is critical, is equal to the next element down diagonally in the opposite direction. So if you're moving southeast, right? So if you're moving southeast in this case, then it is on the west side, and if you're moving southwest, then it is on the east side. So that is in the opposite direction. Mathematically, you can relate them with the term numbers, correct? So if I write T44 plus T54 plus T64, T74, it is the element T85, which is the result. So that is the diagonally placed element. Similarly, we could also use the combination NCR and choose R combination. You'll soon learn that each element, the value of each element in Pascal's triangle, is also represented by the binomial coefficient. So that makes it extremely useful. So we are soon going to explore that property also. So this is a way of writing. So when we write 5, you should be reading this as 5. Let me say we write 5. We say 5, choose 0. Right? So we use this in probability and also in counting numbers in many different ways for so many real life situations. So we'll soon explore that nomenclature also. Anyway, here is a question based on the pattern given to you. So look at the pattern. The numbers are 5C0, 6C1, 7C2 is equals to 8C2. Similarly, these term numbers are also similar. T44, T54, you get it. So the idea is that this actually gives you the term number here in the Pascal's triangle. So here is an example for you, which is find the value of A and B in this particular expression, which is 10C10 plus 11C10 plus 12C10 plus 13C10. Well, the diagonal is same while you are moving. So what should be the value of A and B? This is another example from one of the test papers. I'd like you to write down this answer. Example 7 is sum of natural numbers. Write an expression for the sum of natural numbers from this hockey stick identity. Well, you've already seen this is the magic, and that gives you the sum of natural numbers. Correct? You can see, where will it be always? It will always be at T, that diagonal on the right. Correct? So accordingly, name it in this fashion, which is term number fashion or binomial coefficient fashion. So I've left that for you to answer now. Let's move on and take the next example, which is example 8. Here is a huge property of Pascal's triangle. Here we say number of paths. So you can actually calculate the number of paths for a lot of movements. Explore the number of shortest grid paths from the given node to the top. So we are given, let's say, position 4. You have to go to the top from 4 to 1. How many ways can you go from 4 to 1? That is the question, right? So as shown here, to go from 4 to 1, that could be one path. This is the next path. This is the next path. And then that is the last path. If you are moving up diagonally, right? In that case, these are the 4 shortest paths. That is what it means, right? So they take 1, 2, 3, 4 steps to reach from 4 to 1. And how many paths are there? The number itself, which is 4. You get the idea. So in Pascal's triangle, the number itself tells you the number of paths. Well, it could be read the other way also. That is to say that if you want to come from this to some position here, then there are 10 ways of reaching this position. So that means what? This really means that there are 10 ways to reach from one on top, right? One top, right? So from the top, there are 10 ways to reach here. So either way it could work. You get the idea. So this is a huge property which can be utilized in so many ways. Now, so you need to move diagonally up for the shortest grid. This is what we saw from any position. The number itself tells you there are so many ways are there. So entering the Pascal's triangle provide the number of shortest paths to the top. That is what the nutshell thing is. 4 paths are there as shown from the node with entry 4 to the top. Correct? So those are the 4 paths. Now based on this, here is another exam question for you. Exam question number 2 for you is, in the arrangement of letters, start from the top and proceed to the next row by moving diagonally left or right. How many different paths will spell each word? So try to find the paths to London as shown here, one of the paths. So basically you have to reach this particular point, and there are 2 points where you could reach. How many possible paths are there? Maximum possible paths are there, which are shortest from L to N, moving diagonally downwards in this Pascal's triangle. So you need to figure this out. Well, of course, we have to find the number. So to find the number, what should you do? Well, we can begin by 1 on the corners, correct? So we can place ones on the corners, correct? That is one thing. And then we can place the numbers inside by adding the previous 2. So this is number 2, that is 1. And then you have this number as 3. This number will be 3. Add the previous 2, right? This is 1. And then when you add further, so it is 1 and 4, correct? And then we add 3 and 3 to get 6. 6 plus 1 is 4. Well, those crosses, you cannot go there. So those are your boundaries. Well, now 6 plus 4 is 10 and 6 plus 4 is 10. So for this particular case, the result is 10 plus 10, which is 20 paths. So here we get 20 ways of going from the top position to the last two positions shown here. Do you see how we can do it? I'd like you to follow this particular pattern and practice with one of these examples. That should be good. So here the answer is 20. And that is how you could answer for the others also. So copy this pattern, write down the numbers, and the number itself which you get at the end, add them all to get the final result. So I hope that is absolutely clear. Now let's move on and take the next example, which is application of Pascal's triangle to binomial expansion. Correct. So once again, we have the same Pascal's triangle starting with 1. We have 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1. Well, does that remind you of expansion? Well, if I have a plus b to the power of 0, what I get is just 1, correct? But if I have a plus b to the power of 1, I get a plus b, and a plus b whole square is a square plus 2ab plus b square. Well, now start comparing. So you see this 1, 2, 1, and here you see 1, 2, 1, correct? 1, 2, 1 are the coefficients right there. Next line here is cube, and there you go. So what do you see the coefficient as? 1, 3, 3, 1. Those are the numbers in the entries of the Pascal triangle also. 1, 3, 3, 1. Correct? So 1, 3, 3, and 1. Beautiful. Especially all the Pascal triangle entries will match the binomial expansion. So if you move on in this fashion, you can match them up. As you can see, that clearly means that Pascal's numbers, which can be easily generated, can be used to expand binomials, right? So if I have something like this, I mean a plus b to the power of 7, how am I going to do it? Well, clearly, I'm going to use these numbers. Is that clear to you? So if I use these numbers as the coefficients, I can do it. Perfect. And we know some of the properties of binomials, right? When you expand, the exponent sum is always equals to n. So in this case, it will be 7. And it is in a particular order. It is always decreasing for the first term and increasing for the other one so that they add up to 7. So for 7, it will be a to the power of 7 beginning from with coefficient 1. And the next one, the leading coefficient, the next coefficient will be 7. And then 21, and you can easily expand and get your result. Perfect. Now one thing to remember here is that when we talk about combining or relating the Pascal's triangle with the binomial numbers, remember one thing, since we start with 0th row, right, this starts with 0, therefore it is kind of important to understand that if I say that the power is n, then we're looking at n plus 1th row. So when you count the rows, this which is number 2, which is 0 row, is the second row, but it is actually speaking row number 1, 2, and 3rd. So if you count the rows literally, right? So it is the 3rd row, correct? So basically, this becomes the 3rd row by counting the rows. You agree, right? As far as the Pascal's number is concerned, it is adjusted because it starts with 0. But when you say the row number, it is one more. So it is very important to understand that n plus 1th row in Pascal's triangle give coefficient for a plus b to the power of n. Okay, so this is kind of important. So here I've made another table for you to just written the coefficients, right? So for example, a plus b whole cube, the coefficients are 1, 3, 3, 1. Perfect. That is how you could do it. Now, if you want to expand 7, you could have, extend this pattern and get to the 7th row, which will be kind of like this. And then you can easily write down the expansion for 7th power. So binomial coefficients are related with the terms in the Pascal's triangle as we have just learned. Now question number 1, based on the binomial expansion is, state the row of the Pascal's triangle that would give me the coefficient of the expansion 2x minus 3 to the power of 24. So when we count the rows, it should be 24 plus 1, 25th row, right? That is how we are going to do it. Okay. Example 9. We're now talking about the iterative formula for the Pascal's triangle. Now, we also introduce you to the coefficients, binomial coefficients, and these binomial coefficients are written in the form of NCR. So we are using that nomenclature NCR and choose R, correct, in this particular case. So, since the binomial coefficients have the correspondence with the terms in the Pascal's triangle, the relation is also written as, so instead of writing the term numbers T, N, R, we are writing NCK, right? So N choose K. So that is how. And you get the elements by adding up the previous two, so N minus 1 and K minus 1 plus N minus 1 K. So those two which are just before will get added to get the next one. So this particular triangle, I've replaced the numbers with the convention N choose K, right? So N choose K, which is written as NCK and choose K in this fashion also. So many different ways of writing this, right? So we also write C and K, right? So that is also another way of writing the same thing. These are the coefficients for a binomial expansion, right? So the very first one will be Cn0, right? It also starts with 0. And in any binomial expansion, if n is 5, the number of terms will be 5 plus 1, which is 6, correct? That's the whole idea. Okay, so now let's moving forward. Here is, we have to read nck as n choose k or nck, you can see, right? So you could also read this as nck, yeah, either way. So here is an example for you which says, if 126C78 is equals to 125C78 plus AB, find A and B. That is the question for you, right? Use your rules. So what should be A? Well, A should be 125 and B should be 1 less than 78. You're adding the previous two, and that's how you can get your answer. Perfect. The next example here is, we have rearranged the formula a bit. We are saying 123C20 equals to 124C20. So it's a bigger number, and therefore we have minus here. We have rearranged. What should be C and D? 1 less than 124, which is 123, and 1 less than 20 also, which is 19. That should be your answer. Perfect. Now, what is the meaning of NCK? Once again, it is a formula which can be used to calculate the binomial coefficients. You can use calculator, and the formula is NCK is n factorial over n minus k factorial plus k factorial times k factorial, right? Now, let's rewrite here. If I write n factorial, it really means n times n minus 1 times n minus 2 times so on, right? So times 3 times 2 times 1. So that is n factorial. Multiplication of n consecutive natural numbers, okay, starting from 1. So that is what is the meaning of n factorial. So NCK, the formula is given to you. You can always use calculator to calculate these values. For smaller numbers, Pascal triangle is a good option. Now let's move on and take the next example. Now we were talking about many symmetries, right? So we did notice a particular symmetry which is called row symmetry, right? So row symmetry is that each element you will see they have the same values. So NCK is equals to NC n minus k. So the values positioned from left side and from the right side are symmetrical, and that is what is the major property. Correct. So using this property, we have a question for you. You can always pause this video, answer the question, and then move on. If NC9 equals to NC3, find the value of n. Okay, so this is what you have to do. How are you going to find the value of n? So n means it is symmetrical from both the sides. There are a couple of ways to do it. One way is you can write n is 9 plus 3. That is one way of doing it. The other way here is, since that means n minus 9 should be equals to n minus 3, right? So because it is symmetric from both the sides, you have to choose a number so that you get the same result, right? So that is the whole idea. So 12 minus this n minus 3. So n plus 3 is the best way to do it. You can add this up, you get 12. So you see 12 minus 9 is equal to 3, correct? That is how you can get it, and that is how we should be doing it. And also 12 minus 3 is equal to 9. So it works both ways. That is what we're trying to figure out. So that number n is the sum of 3 and 9, as you have seen here. Perfect. That is how we'll figure it out. Now let's look into example 11, which is 20c16 equals to 20ck. Find the value of k, where k is not 16. What should it be? It has to be the difference between 20 and 16, as you now know, right? So you can say this is 20 minus 16, which is equal to 4. And that is how you're going to answer this question. And this is from the property, which is the row symmetry property. Perfect. Now here is a different look of the same triangle. Now if I left align all the values or the terms in the triangle, it will look exactly like this. So what I've done, instead of that triangular form, I put them in rows and columns. Makes sense, right? It is easy to see many patterns here. So have a close look at this rows and columns. So I have written the binomial coefficients in terms of the term numbers right on the top, since binomial coefficients and the term numbers have exactly the same value and they can be replaced. And so we'll keep on switching from binomial coefficients to Pascal's triangle and Pascal's triangle to binomial coefficient terms. Okay. As you can see here, we have ones on the boundary, correct? So those are the ones which we're talking about. That is the boundary for us. And in between numbers, you can get by addition. Do you see that? 6 plus 4 is 10, 35 plus 35 is 70, and 28 plus 8 is 36. So you can always sum the closest to, right, from the left side, in this case now, to get the next number in your pattern, correct? That is how we get it. Now here are a few more interesting things. We did them last time. If we add each element in the row. So see, 1 that adds to 1. 1 plus 1 is 2. 1, 2 and 1 gives you 4. So you see that you get all the perfect squares here. So all these numbers are perfect squares. And that's what I mentioned here, that the sum of elements in the row is 2 to the power of n. Correct? Also, you will notice that the value of n and the value of k should be a natural number where n is greater than k or equal to k, right? So k value is from 0 to n, correct? But if the denominator is n is more than greater than 0, you can see it's a blank space here, correct? That is kind of important to understand. Now, if I have something like 0 CR, its value is always 0. That is what we're trying to say here, as shown in this light blue color right on the top, right? So this is where we are choosing something from nothing, and that is not possible. So you get 0 there, right? Now, the combination formula was the same as the iterative formula for Pascal's triangle. N choose R is equal to n minus 1 choose R minus 1 plus n minus 1 choose R. Correct? N has to be greater than equal to 1 in this particular case. So that is another way of representing the same Pascal's triangle, and you can now figure out many other patterns from here. Correct? So that is very interesting. Now you can see that there are some columns. We are talking about perfect squares. 1 plus 3 is 4, correct? 15 plus 21 is 36. These are perfect squares, and that is NC2. So NC2, if you move into different rows, add them together, you get a perfect square. So you can have a formula for reading perfect squares from Pascal's triangle, right? Let's move on and explore further. Well, hockey stick property we did, correct? Also, notice here, if I add these numbers in the particular row, in the particular column, correct? Starting from 1, of course, then the sum is given in the next column, correct? As shown here. So that is your hockey stick property, which we just talked about. So there are many patterns which can be further explored using this property. So here we could summarize this with a column sum property, that if you add all the columns in the column up to k, then the value will be as shown here. Do you see that part? So sigma for n changing from 0 to n for kc is equals to n plus 1 choose c plus 1, where c is greater than or equal to 0. Now row sum property. As we explored, we know that the sum of all the elements in a row is 2 to the power of n. Now based on this, here is example 12 for you. Find the sum of all its terms in row 15th of Pascal's triangle where n is equals to 15. So if n is 15, then it is 2 to the power of 15, correct? So you get your answer. So just write 2 to the power of 15, calculate, get the answer. Example 13. Which row in Pascal's triangle has the sum of all the terms equal to 4096? Right. So, you know 2 to the power of 10 is how much? 2 to the power of 10 is 1024. That should help you to get this particular answer. So times 2 times 2. So 2 to the power of 12 is the answer for this. Many times calculator is not allowed for this exercise, and therefore it is kind of critical to know some numbers. Here is the next question for you, which is sum of entries for alternate signs. So we are now changing the signs from positive to negative. Do you see those negative signs which we have written here? So all these highlighted signs, it's very small for you. So I'm just highlighting these are the negative signs. So if I substitute keeping the first as positive and then alternate with negatives, then what happens? Then when you add some of the entries, then all the entries will be 0 except for the first one. So this will sum to 1, but all the others will sum to 0 because positive and negative from the symmetry itself will cancel out. And therefore, we have this particular property that sum with the alternate signs will either be 1, and that will be only when n equals to 0 in Pascal's triangle, or will be 0 when n is not equal to 0. Perfect. That is how we do it. And based on this, here is an example for you. There are actually two questions here to solve. One is here to add the numbers from 0 to 100 minus 1 to the power of k, c, 100k, and the sum is 0. And part B is add 50 minus 5c1 plus 5 choose 2 minus 5 choose 3 plus 5 choose 4 plus 5c choose 5, right? So you have all this thing written here. So I think I wrote a sign wrong. So minus plus minus plus, and that should be minus clearly. And then you get 0. If I don't write minus, you don't get 0, right? So anyway, so either way, work it carefully. Next number here is sum of the first n natural numbers. So we are actually taking some very important questions. These are test questions based on what we have learned so far. So this will kind of review what you have learned. So I'd like you to read the question, answer, and then check with my solution. So what are the sum of n natural numbers and how can you relate them? Clearly, these are the natural numbers 1, 2, 3, 4, and hockey stick property tells you that the sum lies on this side. Do you see that? Sum of first 7 numbers is 28, and that helps you to write down the formula, correct? So we see that n plus 1 choose 2 is the answer for the sum of natural numbers of n, correct? So it is the second diagonal which will be holding the sum as highlighted here. So 2 is the second diagonal, and one more, the next row, and therefore next row, second diagonal. So let me write down here what we have here is next row and second diagonal. So we have this formula n plus 1 choose 2 as the answer. You can use this to find sum of, let's say, 100 natural numbers will be 100 plus 1, which is 101, choose 2. And using the formula, which is right there for calculating the coefficients, you can actually get the answer, right? Now here we'll explore further another property, which is sum of two numbers in Pascal's triangle can give you a perfect square. As we were seeing, the diagonal 3 is the key, right? So diagonal 3. So if you analyze diagonal 3, which gives you all the triangle numbers, if you add 3 and 6, for example, what do you get? 3 plus 6 is 9, which is the perfect square, right? This is 9. And 10 plus 15 is 25. And 21 plus 28 is 36. And 28 plus 36 is what? Is 6 and 8 is 14 and 1, 64. And you see these are all perfect squares. Perfect. And that is how you could get perfect squares by adding two elements, the value of two elements along the third diagonal, right? So the formula here is what gives you the perfect square. So n squared is n choose 2 plus n plus 1 choose 2. The third diagonal is second diagonal on the Pascal's triangle. So n choose 2 plus n plus 1 choose 2, where n is greater than 1, gives you the result. Well, the next example here is sum of squares. So we are extending now from just the number sum to their square sum. And the formula here given to you is very important. You can make a note of this particular formula. It will be very useful. So when you want to add the sum of squares, you could actually get from 2n, choose n. So 2 times the row number will give you the right answer, right? So that is the formula which can be used. Now the question here is, show that the sum, sigma notation I hope you are very clear with, where k changes from 0 to 3, 3 choose k whole square. So every number you have to square, right? 3 choose k is this particular row we are talking about. The numbers are 1, 3, 3, 1. And when you square them, 1, 3, 3, 1, you get 20 as their sum. That is the value. On the right side, if we have twice n, in that case, we're looking at 6 choose 3. 6 choose 3 is the value right there, which is also 20, right? So we see that we do get the result immediately from the Pascal's triangle itself. And that is what we're trying to say here. And we have a formula to relate it. So that is how we can do it. Here is an examination question for you. You can now evaluate what is 9 choose 2 plus 10 choose 2, right? So this is based on previous slide which we took. So I'd like you to answer this particular question. So let's move forward and take the next part of this particular section, which is example 17 for us. So in example 17, we are again exploring the sum of squares of any row using the same formula. So if you are summing the squares of the elements, in that case 2ncn is your value. So example 17 is, determine the sum of squares of the sixth row of Pascal's triangle. Not the sum of numbers, but sum of squares of those elements, right? So that is the question for you. You can pause the video, answer this question, and then look into my suggestions. Perfect. The solution is given to you. Twice 5 we are doing. You know why? The sixth row is actually n equals to 5, right? So first row, second, third, fourth, fifth, sixth, and you'll see this is written row number 5 for Pascal's triangle. So therefore that is critical part, and once you do that adjustment, then you get your answer. So here is an examination question where we are written in the binomial coefficient form. So it is 2 times square of C6C0 plus square of 6C1 square of 6C2, everything multiplied twice, plus square of 6C3. Find the sum of this particular expression. The next question here is another very important observation. which was seen, and now it is called the Star of David theorem, discovered by Henry W. Gould in 1972. So in this particular pattern, Pascal's triangle, you notice that if you connect the elements in the form of a star as shown here, the elements which are connected as 20, 21 and 70, and then we have 35, 15 and 56, their product is exactly same. So that is what this is. So what we're trying to say here is that the product of 20 times 21 times 70 is equal to, so the product of 20 times 21 times 70, which is in this star as shown here, correct, is same as 35 times 15 times 56. So from this position we find that they are exactly same. So you can use the calculator to calculate the value. The value comes out to be 29,400, correct? So for both we get the product as 29,400, and that's a very important property. Now the question for you is, you know this property works. You can take any particular situation and you will see that it really works. For example, here you could color taking, let's take a simple one. Let's skip this 4 here, right? So 1, 6 and 1. When you multiply these, you get what? You get just 6, correct? On the other hand, you can have the numbers which are diagonally placed, and then you can actually, when you get this number, the placement will be 4, the top value is 3 and 1. This was the wrong number selected. Well, the number should have been 5, correct? Oh, sorry. So let's redo it. The number should have been not that one, this 5, right? So we're looking at 4 in the center. So first mark a number in the center. Let's say we are looking at numbers around this particular 4. So we looked at number around 35. So those are the star elements being placed, correct? And then these other star values are these, correct? When you multiply, what do you get? You get 30 for each, right? That is what I'm trying to say. So easy calculation. You can make your stars and then you'll find that it really works, right? So when you make the star here and then with these numbers, you find that their product is exactly same. In this case, it happens to be 30, correct? That is what it means. Now let's move on and see how can we write this in the combination form. So we have taken an example here, the same one. So that was 35 in the center is actually 7 choose 4, and those other elements are written there in their combination form, right? And when you multiply them as shown here, the left side is equals to right side, and 2 different colors as shown here, you could always get the same product. Perfect. So that is how you could do it. Now you could generalize this in a particular formula which is given on this particular page. So you can actually pause the video at this stage, write down the formula, and it's a very useful formula from test point of view, and normally not mentioned in books. So that will really help you to understand the whole formula and how you come to this. Perfect. So make some patterns and then figure it out. For example, you can now choose a number, let's say 6, correct? And diagonally placed numbers will be, so you could choose a number which could be diagonally placed. So when you're taking a number here, so on the top side, the bottom side, and on this side, so these are diagonally placed, whose product is 4 times 3 times 10, which is 120, for example, correct? Now we can take another set of numbers which could be 4, 3 and 10. Those, then they fill it up, right? And this sum is again 4 times 3 times 10, which is also 120. As you can clearly see, it works for all the numbers in the Pascal's triangle. You get the idea. So I have already shaded another triangle. I'd like you to write down those numbers in the form of n choose r and your statement. I hope that will help. So here we will end our lesson on Pascal's triangle. I hope you find it interesting and useful. You can always visit our website, which is globalmathsinstitute.com, or could write to me an email if you want to learn from me. So looking forward for your responses. Feel free to write your comments, share your views, and if you like and subscribe to my videos, that'd be great. Thanks for your time and all the best.